So let's work on some word problems with differential equations. And the first question says, a population of rabbits in the field grows according to the differential equation dp over dt equals 1 over 2p, where t is the time in months, and the initial population was 40 rabbits. And part A says, write an equation for p in terms of t. So all we have to do here is just isolate p. And just from this equation, I see that we can separate these variables. So let me just write out the equation again. So dp over dt equals 1 over 2p. And then now we're going to divide p on both sides. So now we get 1 over p dp equals, and we're also going to move dt to the other side. So we get 1 over 2 dt. Now we can integrate both sides to get rid of the dp and isolate p. So integral on both sides, and the integral of 1 over p is just ln p equals, this is just going to be 1 over 2 t plus c. And now to get rid of the ln, we're going to make both sides the exponent with base e. So e, and this gets canceled off, so this just becomes p equals e to the 1 over 2 t plus c. And since c is just a constant, we can move it down to be multiplied by the base. So we can just say p equals c e to the 1 over 2 t. But we're not done yet, because we still have this unknown variable, and we can actually solve for it because they gave that the initial population was 40 rabbits. And initial population means that no time has passed, so time is 0. And they say that 40 rabbits. So basically we have a point where t equals 0 and p is equal to 40. So now we can solve for this unknown. So 40 equals c e to the 1 over 2 times 0 is just 0, and e to the 0 is 1. So c equals 40. So now I can fully write the equation. P equals 40 e to the 1 over 2 t. And this is our final answer. Part B, we have find the rabbit population after 6 months. So from part A, we have our equation p equals 40 e to the 1 over 2 t. And now they're saying find p given that 6 months has passed. So t equals 6. So p equals 40 e to the 1 over 2 times 6 is 3. And if you want an exact answer, you can leave it as this. But if you plug this into your calculator, this is equal to around 803 rabbits. And this is our final answer. Question 2, we have, when a transistor radio is switched off, the current I in milliamps falls away according to the differential equation di over dt equals negative 0.4 I, where t is the time in milliseconds. At the instant the radio is switched off, the current is 350 milliamps. For part A, it says write an equation for I in terms of t. So we have to do basically the exact same thing as question 1. So let's do that. So di over dt equals negative 0.4 I. And we're going to divide both sides by I and move dt to the other side. So we get, and we're going to keep negative 0.4 there. So we're going to get 1 over I di equals negative 0.4 dt. And now we're going to integrate both sides. So this becomes ln I equals negative 0.4 t plus c. And we're going to exponentiate both sides. So we get I equals, and we're going to move c down to be multiplied by the base. So c e to the negative 0.4 t. And we're also given that at time is 0, I is 350. So 350 equals, let me just write that, t equals 0, I equals 350. 350 equals c e to the negative 0.4 times 0. So this becomes 1. E to the 0 is 1. So C equals 1. C equals 350. So the final equation is I equals 350 e to the negative 0.4 t. And this is our final answer. 2b, we have find the current after 5 milliseconds. So basically what we have to do is from our equation, I equals 350 e to the negative 0.4 t. All we have to do is plug in t equals 5 to find the current. So I equals 350 e to the negative 0.4 times 5 is negative 2. And this is the exact answer, but if you plug this into a calculator, you'll get 47.4, and the units are milliamps. And this is the final answer. Part C, we have how long will it take for the current to fall to 20 milliamps. So this time we're given the amount of milliamps, but we need to see how long it takes. So from our equation, P equals 350 e to the negative 0.4 t, we have to plug in 20 into our milliamps and solve for t. So this is just going to be 20 equals 350 e to the negative 0.4 t. Now we have to isolate t. So we can divide both sides by 350 to get e to the negative 0.4 t equals 2 over 35. Now we can ln both sides to get negative 0.4 t equals ln 2 over 35. And then now we can divide both sides by negative 0.4 to get t equals ln 2 over 35 divided by negative 0.4. And this is the exact answer, but if you put this into a calculator, you'll get 71.6, and the units are milliseconds. And this is the final answer. Question 3, we have radium-226 loses its mass at a rate that is directly proportional to its mass. If its half-life is 1590 years, and if we start with the sample of radium-226 with a mass of 100 milligrams, part A, we have find the formula for the mass that remains after t years. So for this question, we need to understand that when the rate of change of a quantity is directly proportional to the quantity itself, mathematically we have to state this as dy over dt equals ky, where k in the right hand side, with the k is either a growth or a decay constant. So with that information, we can solve for y here, which will be the mass, and t is the time, and k is the constant that's either growth or decay. So what we have to do here is divide both sides by y. So we get 1 over y dy is equal to k dt. Take the integral of both sides. ln y equals kt plus c. And we exponentiate both sides, so we get y is equal to, we're going to move c onto the other side as well. So y equals c e to the kt. Now for this, we are also given that we start with the sample of radium-226 with a mass of 100. So we're given that when t is 0, no time has passed, the amount of mass is 100. So 100 equals c e to the k times 0 is just 0, so it's 0. So e to the 0 is 1, so c is 100, but we're still not done yet. Now we have y equals 100 e to the kt. But now we need to solve for k, which is the growth or decay constant. And we have more information to solve for that, because it says if its half-life is 1590 years, half-life means that literally half-life, half of the life it started with. If it started with 100 milligrams, its half of that is 50. And they say that it reaches a half-life after 1590 years. So we're going to set y equal to the half-life, and the half-life is just 100 divided by 2 because this is because it's given to us, it starts with a mass of 100. So 50 equals 100 e to the k times 1590. Now we need to just solve for k. And first we're going to divide by 100, so we get 1 over 2 equals e to the 1590k. ln both sides, so we get ln 1 over 2 equals 1590k. So k is equal to ln, let's just say 0.5 over 1590. Now we have all of our unknown variables. So this is going to be the formula for the mass that remains after 2 years is y equals 100 e to the ln 0.5 over 1590. Hold on, that's a weird zero. T. And this is our final answer. Part B, we have find the mass after 1,000 years. So from our equation, y equals 100 e to the ln 0.5 over 1590 t. We basically have to replace t with 1,000 and solve for y. So y equals 100 e to the ln 0.5 over 1590 times 1,000. So this is the exact answer, but if you plug this into your calculator, you'll get 64.7 years. And this is the final answer. Part C, we have when will the mass be reduced to 30 milligrams? So basically, instead of given the time, we're given the mass, and we have to find how long it will take to get to 30 milligrams. So from y equals 100 e to the ln 0.5 over 1590 t, we basically have to replace y with 30. So 30 equals 100 e to the ln 0.5 over 1590 t, and divide both sides by 100 to get 0.3 equals this. And then now we have to ln both sides, so ln, and this is going to equal ln 0.3 equals ln 0.5 t over 1590. And then now you divide the whole thing by ln 0.5 over 1590. So this is going to be 1590 ln 0.3 divided by ln 0.5, and this is t for exact, and the if you plug this into your calculator, you'll get 276, around 2762, and the units are years. And this is the final answer.